SwayamPrabha. Digital India. Educated India.
Welcome to today's lecture. We just started our discussion on the environmental impact of mineral resource exploitation, and today we will have a brief discussion on one of the issues, one of the known impact of mineral resource exploitation, particularly pertaining to the multimetal sulfide deposits, metal sulfide deposits who have been the major source of base metals like copper, lead and zinc in the world, and those deposits which are essentially worked by open pit methods, and in that process the environmental the impact or the way the environment is affected is by a process which is known as the acid rock drainage or acid mine drainage. And as we discussed before, that such kind of situation arises when a metal sulfide ore body is exposed during the process of open pit mining to atmosphere, and essentially the atmospheric oxygen and the moisture that leads to the oxidation of the sulfide minerals, generation of copious amount of sulfate ion and the H plus, which decreases the pH of the fluid of the water. That is how the name is derived from acid mine, but this the water is rendered very acidic, pH becomes very low, and the problem is that in addition to the fact that such acidic water, when released or discharged to the local to the surrounding water bodies in terms of stagnant water body or flowing water body, they will affect the biota, they affect the ecology of the area. And in addition to that, when the water becomes very low pH, its solubility of different metals becomes high, as we all know, and in that process it also dissipates or it also mobilizes lots of toxic metals. For example, if the particular deposit has a high concentration of lead and cadmium or any other heavy metals, then these metals also get dissolved in this kind of acid mine water and is dispersed into the surrounding areas, contaminating the soil and water. And if it happens for a good number of years, then it affects in degradation of the quality of the overall quality of the area. And as we discussed before in the last class, the processing of such kind of metal sulfide ore bodies in the flotation process, in the concentration process, which give rise to the waste in the form of tailings, and the tailings are accumulated in structures like tailing dams. They are essentially not dam the way we know them, but they are areas where the geology, in terms of the topography, the conditions are favorable, where this tailing could be deposited, and it could sustain such kind of deposition for a good number of years for the life of the mine. And there is definitely some amount of engineering which is involved there. So these tailing which keeps on accumulating to quite a great thickness, they do also can, and by virtue of the concentration of even the lower concentration of the sulfide minerals, they do also get oxidized, and the pore fluid in the tailing dam will percolate down, eventually contaminating the groundwater. If we go just to understand the process, which is almost very similar to the one which we saw in the supergene oxidation and sulfide, secondary sulfide enrichment process kind of reactions, where a pyrite molecule is oxidized within the presence of water to give rise to Fe2 plus sulfate ion plus 2H plus. Further, this Fe2 plus is again oxidized in the presence of H plus to give rise to Fe3 plus half water, and this Fe3 plus, when it is oxidized, so it gives rise to iron hydroxide, which will be in the form of either a amorphous or very cryptocrystalline form like a ferrihydrite, or it could be goethite, and which releases further hydrogen ions. So, if we combine these reactions, we will see that for a molecule of pyrite, when it undergoes such kind of reactions, chain reaction, then it gives rise to a good number of hydrogen ion, about 1 mole of pyrite will give rise to about 4 moles of hydrogen ion. So, this could go on in an inorganic oxidation process, which will give rise to this acidity and which cause the. So, whenever this water, this surface water is flowing in form of drainage and are being pumped out of the open cast mine site, so they will be eventually be getting discharged into some local water bodies. So, what is more important to know here is that such kind of problems are more acute in case of abandoned sulfide mines than the presently working mines, because of the fact that the longer the duration for which these ore bodies are getting exposed to the atmosphere, higher is the amount of this kind of acidic water which is being discharged. Now, interestingly, such kind of processes are very well accentuated by the microorganisms. The microorganisms are the thiobacillus or the acidothiobacillus or the leptospirillum kind of bacterial species, which survive by the process of this oxidation of this sulfide, the energy which is liberated in this process. We of course, in this simple chemical reactions, we are not representing how much of energy is liberated in this, but it is observed that the energy in terms of calorie which is liberated in such kind of reactions is pretty significant, and it is enough for this kind of organisms for their survival. So, if we look at such kind of process which is accentuated by, so essentially this overall reaction involving the iron 3 plus as a very strong oxidant here. So, then this reaction is giving rise to the iron 2 plus and sulfate plus 16H plus. This could be this reaction could go on in a with the help of this bacteria. So, since we have this kind of bacteria in growing in the natural environment, such bacteria have been identified, been isolated, and very well known for their role in generating this acid mine drainage. So, these are some of the photographs which you can see here. Any abundant or any working sulfide, multimetal sulfide mine, if you visit, you will see such kind of features, which is this water is almost getting a hue of such yellow color because of this particulate matter which is within this water, which is called the ochres. The red, they are called the ochres. They are called the ochre, and in American literature they are called the yellow boys or the bad boys, yellow boys, these ochres or these ochreous precipitates. So, these ochreous precipitates are essentially constituted of so many cryptocrystalline species of iron sulfate, iron oxides, and many other type of different secondary mineral species which form in this kind of environment. So, essentially the pH in this environment is very low. We will see the range in which such kind of pH variation takes place, and under such kind of very low pH, many secondary mineral species come into existence, which of course have their stabilities pretty limited, but they do play a significant role in mobilizing many of the heavy metals and the toxic metals in the environment. So these are some of the features, and many such pictures could be seen available in public domain, such kind of features as acid mine drainage and such kind of aqueous precipitates. So these are this is the way in which the process could be represented chemically on an EHPH diagram. These are some of the commonly occurring sulphate mineral species which are associated with acid mine drainage. Some of them which you are already quite familiar, such as this alunite, which we have seen they form in very low pH conditions in the advanced argillic alteration in porphyry copper deposits. So we know what they are. So they do form in a very low pH condition, and we do also see and such kind of mineral phases which we list, even some of them, or there are many more of them, secondary sulfates as well as sometimes silicates and hydroxides, iron aluminum hydroxides when they form. So these mineral phases are essentially identified by techniques like an X-ray diffractometer. They cannot be studied under the microscope. They possess very interesting surface features, and they are identified based on their by X-ray diffractometry or some spectroscopic studies, in addition to studying their surface micro features with the help of a scanning electron microscope. And this is the antilerite, copper sulphate, hydrated copper sulphate, brocanthite. This is again hydrated copper sulphate. Copiapite is a very specific mineral associated with acid mine drainage. Jarosite is a very interesting mineral, and ophlite is a mineral of much greater interest because of occurrence in Mars and indicating presence of water and indicating very low pH. And the melantorite, rosenite and schwarzmannite. Schwarzmannite is also a mineral phase which is very regularly encountered in the acid mine drainage environment at very low pH. So here it is a PE versus pH diagram, where you can translate the pH to the EH could be something about minus 0.6 to plus 0.6 or plus 0.8 kind of value that we saw before. So within this EHPH range, this different mineral species, their stabilities could be delineated. So this is jarosite, JT is for jarosite. This is the schwarzmannite. This is the FH is for ferrihydrite, which is essentially is a cryptocrystalline or an amorphous form of FeOH3, which forms and then it helps in generation of a lot of H plus ion, which again we have seen this reaction. So this is the natural limit of EHPH. So this as you could see very clearly that minerals like secondary sulfate minerals like jarosite and schwarzmannite, and this is for goethite, which forms in this range, and it always we could see that the higher the oxidation state and at very low pH, which very much corresponds to the environment that prevails in a in an open pit sulphide mine. So these are the mineral species which generally are there. So here we could see as the actual scenario. So there is certain. So now the question is whether it is only pyrite or any other sulphides. Other sulphides also do get sulfide oxidized. They do generate the sulfate ion and the H plus ion, and they do also. But then the most important culprit in acid mine drainage is actually pyrite. So if as we saw before, a pyrite, 1 mole of pyrite will essentially be generating 4 moles of H plus, and marcasite is just a polymorph of pyrite, which is also FeS2 in its composition, and in most of the properties and in terms of its kinetics of oxidative reactions, it is almost similar to pyrite. So, pyrite and marcasite, these two are the ones which generate the maximum amount of H plus ion and imparting acidity to the water. Arsenopyrite releases 2 moles of H plus ions. Chalcopyrite also we have seen such kind of reactions, chalcopyrite with oxidation in presence of water, it also will release copper 2 plus ion, sulphate ion, and also iron. Pyrrhotite is rather as a source of generation of the acid mine drainage. It generates about almost 0 to 2 depending on what form it is, and sometimes the textural characteristics of the pyrite also is important. If there are very fine grained rhomboidal type of pyrite, they do generate more of acids, they get oxidized much more faster, quicker. And then in terms of the rate of the reactions and the generation of the pH, the acidity is concerned, and energite, which is a silver sulphide, which gives only 1 mole of hydrogen, and minerals like galena and sphalerite, they almost are very negligible contributors to acid mine drainage. So, the main culprit in acid mine drainage is pyrite and marcasite. So, any pyrite which, as we saw before, when it comes to a secondary supergene oxidation and sulphide enrichment process, a pyrite rich ore body will always give rise to this process much more efficiently than a pyrite poor ore body, and where the pyrite abundance will be less, there the surface oxidation does not proceed to that completion, and we get a lot of copper trapped in the oxidation zone. Anyway, so these are the species, and the iron bearing species are represented here. So, the iron 3 plus, iron OH 2 plus, and where the H plus ion consumption is given in terms of 1, 2, minus 3, and the log K, the equilibrium constant values when the I is here is the ionic strength is about 3 molal, and Fe3 concentration is almost 1, and here these are the iron bearing species, and also as you could see the liberation of the H plus ions is shown here. FeOH 2 plus is 1, FeOH 2 plus with Fe3 plus is depending on the concentration of iron and the nature of the molecule and the availability of water. It also releases 2 moles of hydrogen ion, and in this case it is 3 moles of hydrogen ion, and we see FeOH 4 plus, FeOH 4 plus. So, they are generating different amount of the H plus ions, different molalities of the H plus ions. And so, these are the again you can see the same reaction over here. This is the amorphous iron oxide, this is ferrihydrite, amorphous FeOH3 solid. So, that is here it is forming through this reaction liberating 3 moles of H plus ion, and when it is formed in a cryptocrystalline ferrihydrite form forming from iron 3 plus, it is giving rise to a form of hydrated iron oxide limonite and generating H plus ion. Goethite is again similarly generating the H plus ion, hematite, and this one is the swartmanite. When this swartmanite forms also it generates H plus ion. So, we can see that in a very strongly acidic environment such kind of minerals they are forming. So, swartmanite can be written in 2 different ways. So, this is jarosite. Now, what exactly happens? We can see through this kind of reaction that suppose this is the formation of goethite from this compound, which is your alunite, jarosite. So, jarosite forming, so as you have seen before in the diagram, with increasing pH, jarosite gets converted to ferrihydrite with increasing pH. So, if we see that, so this particular goethite, this jarosite is with increase in the pH is getting converted to goethite. This is the goethite, and goethite again this is same, this swartmanite, which is getting which is again when it is getting converted to goethite, it also releases H plus ion, and again the same swartmanite, depending on what the way we are writing the formula and availability of water. So, the diagram that we saw before in the EHPS diagram, the stability, we can understand that these minerals like jarosite and swartmanite with increasing pH gives rise to gets changed over to iron hydroxide phases. Now, the important thing about them is that this can also happen with decreasing moisture, or the situation becoming more drier, or even temperature is higher, and also the pH of the surrounding is changing by interaction with the surrounding rock. So, what happens is that such kind of minerals like jarosite and swartmanite, they are very fine grained. So, with a lot of available surface area and their typical surface features, they do have lots of other heavy metals adsorbed onto their surfaces. So, as and when such kind of mineral phases are getting transformed to iron hydroxide phases, the adsorbed metals, heavy metals get released. So, these minerals, they, even though they themselves are not the culprit, but they are very much so when they are generated at the acid mine drainage generation site, and when these are the secondary minerals that are forming from the or precipitating from the fluid and carried in solution or in the form of suspension in cryptocrystalline state, a very fine grained state, they do have a lots of other toxic metals, heavy metals adsorbed onto their surfaces. So, as and when they get converted to the iron hydroxide phases like ferrihydrite or goethite, these ferrihydrite and goethite cannot accommodate these toxic metals on their surface the way these minerals are able to accommodate through the process of adsorption. So, adsorption desorption plays a very important role in mobility of the heavy metals and their dispersal in the surroundings. So, the moment these minerals are getting converted to such iron hydroxide phases, these heavy metals are again released into the surrounding. So, we can see through this schematic reaction as to what exactly happens or the chemical control. So, this gives us some of the idea as to the process of oxidation of the primary iron sulfide minerals by oxygen, where we could see that pyrrhotite where it gives rise to 2 H plus, and so it is basically is an incomplete reaction which is written for pyrite, but this again we know that this Fe2 plus will be acted upon by Fe3 plus, and then the amount of total hydrogen that will be released will be 4 H plus. So, now we can see that what will happen to this iron 2 plus that is released here. In the process of the oxidation, the iron 2 plus that is released in this reaction, what happens to them? So, the fate of iron 2 plus. So, one is that it may be that there is no further oxidation to the iron, and in that case the iron will only get combined with the sulphate to form the hydrated sulphite, which is melanterite, is one of the secondary sulphate which we list before. And such kind of phases like melanterite, if the situation is becoming a little drier or the temperature increases, they get converted to phases like rosenite, where you could see that its iron sulphate 4H2 and 3 water molecule is released. If this particular iron 2 plus is undergoes oxidation either by biotic with the help of the bacteria which are surviving at pH, very low pH is pH less than 4, and abiotic where pH is greater than 4, slightly less acidic condition than biotic condition. So, we can write the reaction like Fe2 plus oxygen plus water is Fe3 plus 0.5 water. Okay. So, what happens to the fate of iron 3 plus, which is coming out by the oxidation process of this Fe2 plus, means this Fe2 plus which is liberated here can either be it may not be further oxidized depending on the prevailing environment, or it can get oxidized either in a biotic or an abiotic method giving rise to Fe3 plus. So, what happens to the fate of Fe3 plus? So, either it could undergo some precipitation of salt, ferric or mixed valence state, which we just saw the mineral copiapite, which forms just from the Fe3 plus ion in a situation which could be represented by reaction like this. So, this is a simple salt precipitation in which it could be in both 2 plus and 3 plus state. So, it could be mixed valence state. It could either it could also undergo a hydrolysis and ochre precipitation. So, what we represented as ochre is a combination, as I told you, that ochre, which is the suspended particular matter which is present in the water which is coming at acid mine drainage with its typical color that we saw from the photographs. So, these are the ochreous precipitates or the phases which are in ochre: xerosite, swatmanite and ferrihydrite. So, these are the situations in which, if depending on the sulphate concentration, if the sulphate concentration is more than 3000 microgram per liter, microgram per milliliter, and if there is some availability of potash ion from the silicates in the surrounding rock, then it forms the xerosite. So, the essential condition for formation of xerosite is definitely pH should be very low, almost about 1.5 to 3, and under such kind of a very low pH with availability of potassium from these common rocks, it forms xerosite. If the pH is a little high between 3 to 4 and the sulphate concentration is something between 1000 to 3000 microgram per ml, then it will form a mineral which is the swatmanite, which we just saw before the composition. And if the pH is greater than 5 and the sulphate concentration is falling down much less than even 1000 microgram per ml, then there is formation of ferrihydrite. So, the minerals, the secondary minerals which form in the acid mine drainage could be explained, the mechanism of their formation could be explained in this way, and are very much dependent on the pH of the fluid that is essentially coming out from the what we saw is that such kind of processes are so very expedited and facilitated by microorganisms like bacteria. So, in which there is copious amount of H plus ion that is released to the solution, and the pH can fall down to as low as 1.5 to 3, favoring formation of mineral phases like xerosite or swatmanite. And if the pH is increasing with reaction with the rock where there is a sink available for the H plus ion, then the ferrihydrite will form. They also do form when the situation become less hydrous, and that is how they lose their water molecules and form these phases. So, we will continue discussing on the issue of acid mine drainage a little further, and then take up some other environmental impact issues related to mineral resource exploitation in the next class. Thank you.